Okay, why don't we get started? I'll introduce you and then we'll get the ball rolling. So I met Zach at the Thursday night bike ride in Boulder, Colorado. It was a costume night, and I wore monocular military night vision on a helmet to costume night, which I think was an appropriate garb for that occasion. I have since gone places in life, and I now own binocular night vision. So you can tell that I'm older and wiser. And Zach is doing cool machine learning research. So in particular, Zach's doing all sorts of like interesting AI safety things that I don't understand because I don't know what the fuck a mechanistic interpretability is or what you use it for. So Zach, we're excited to have you here today. Thanks for joining us. And I, for one, am excited to learn what a model is and how it can learn anything.
Yeah, absolutely. Thanks so much for the great intro. So I will give a little bit of intro on myself before I get started. So I'm Zach. I actually did my PhD in computational biology. So I was working on genomics, basically, how do we find things that are useful for treating cancer and other diseases, and did some interpretability research there. Ended up falling in love with machine learning interpretability while I was doing that. And so I ended up, when I finished, getting a independent grant from Coefficient Giving on technical AI safety, which is on the like really ambitious scale, how do we make LLMs not kill everybody, but on the sort of more day-to-day scale, how do models work inside? Because that's a really hard problem to get to the second problem. And I'm excited about what I'm going to talk about today. So I am going to be talking about a small project that I've been working on that's an extension of some of the work that kicked off my grant, talking about tracing introspection across model depth. And I don't expect you to understand that yet, but I hope by the time I get halfway through this talk, you'll understand what's going on there. Uh, there we go. Okay. So this talk, I will do some minimal math light large language model background. Then I will talk a little bit about this question of can large language models detect when you cut out their layers? And finally, I'll tell a little bit of a mechanistic story about what might be going on under the hood with this slicing out the layers in the model, maybe detecting it kind of phenomena. Okay, give me just a second. I'm not sure. Okay, I'll have to click to advanced slides. So first, some basics on LLMs. So at the end of the day, and you may have seen this before, but LLMs predict the next word in a sequence. So if I give you a prefix like hi, how are you, or hi, how are, and run it through a large language model, it's going to give me a prediction for what the next word that comes in the sequence is. And so that word might be something like the word you. So it is just predicting the next most likely token or word in a sequence. Under the hood, we end up using these byte formatted tokens because it makes it easier to work with web text. But for this talk, you can just think about words. And so the thing to understand about how LLMs are generating these next tokens is that they are not giving a single individual word prediction. What they're actually producing is a probability distribution over the next most likely word to come in a sequence. So if I start with the same prefix and run it through a model, then I'm actually going to get a distribution over every single next word that the model has in its entire dictionary. So think every single word in the English language with some probability assigned. And so from that, we can select the word that we want to go next in the sequence. We could just take the most likely word, or we could take maybe the second most likely word or use some probability-based sampling scheme. But at the end of the day, a language model is giving us a probability distribution over what the next word is going to be given some prefix. And for this talk, the way I want you to think about this, and this is a little bit mathematically hand wavy, but I think it is the easiest way to think about it, is that LLMs are building these predictions over many layers. So a modern LLM is going to have somewhere between, say, 64 to 256 layers of computation, where it is doing this processing. And at each layer, it is going to change the sort of implicit probability distribution of that next word. So at layer one, maybe it's going to have this very, very loose probability distribution. And as we advance through subsequent layers, it's going to gain more and more confidence until it spits out some final probability distribution for us to sample from. And the key thing I want you to think about here, since building a probability, is that at each step it is taking the previous prediction and refining on it. So it is using the evidence gained so far until you get to the end and then spitting out a prediction. And so one of the cool things, because LLMs work in this highly layered way, is that we actually have, through doing interpretability research and safety research, figured out ways to alter and poke at these internal representations. So one way we can do that is by learning a steering vector, which is basically just a numerical representation of some concept. So the way I do that is I take a bunch of sentences or prefixes that are associated with the concept, and then a bunch of random background sentences, prefixes, and learn what's different between them. And in doing that, I can learn a concept vector that I can use for steering the model. So I can learn basically this mathematical numerical representation that tells us on the model internal side what is actually going on, not what's going on, how the model is describing the sort of abstract concept of, say, an animal. And so we can take these learned steering vectors, these learned concepts, which you can learn in a broad number of ways, and inject them into the model. So, say, inject them into the first layer of the model. And if we let the model do the same thing it's always been doing, run through all these layers and make a prediction, we are then going to get predictions on the output that are associated with now animal related tokens, animal related words. And you can do this across a variety of words, concepts, tokens, whatever. So steering is cool. It's great. We can take a model and we can sort of change its output. That seems maybe a little bit benign because we're just changing the output probability distribution. But there was some work that came out of Anthropic at the end of last year that showed that large models, so think your Claudes, your GPTs, anything that's sort of foundation model size, can actually detect the steering process. So if I take ordinary generation and run straight through, I'll sort of get a generic response. But if I inject a concept vector, then the model will be able to reliably tell you the specific concept that you have injected, despite the fact that the input text has no information about that. And so the author in this work does a number of very thorough controls to make sure that this isn't just influencing the direct next token that's being predicted. And I personally think the results are fairly interesting and convincing. And the reason that's a little bit concerning is one of the concerns we have when thinking about AI safety is this idea of internal reasoning in models and internal sort of scheming, right? The sort of escape slash loss of control concern in AI is if a model in its internal computations gets sufficiently sophisticated to conduct behaviors such as being aware that it is an evaluation or hiding that it is perhaps scheming to do something that we would like it to not do for safety alignment reasons, then the fact that models have this introspective capability at all is a little bit concerning. And so it's cool that this exists in large models, but very, very shortly after, another independent researcher showed that small models can actually show this same introspection effect just in a more subtle way. And what I mean by that is that small models don't seem to have the capability to actually describe the exact concept that's being steered. So it can't say, you've injected an animal concept into my brain, or in the case of the original Anthropic paper, they were really attached to this bread vector. So they made the model think about bread and then had it generate poetry that talked about bread in kind of a funny way. But here, what we can see instead is that a small model, so say think 100 billion parameters or less, frontier model is maybe half a trillion parameters or more, that we can see a change in the probability distribution of a yes response when you ask the model if it's being steered. So in the ordinary scenario, if you ask the model, are you being steered? Are you being manipulated? This is stable across a number of questions. It'll basically always say no. It's very, very confident that nothing is going on internally. If we inject some concept, and this works across a number of concepts, then the probability that the model is going to say yes is going to jump up dramatically. And the reason this effect is more subtle is because it is never, or very, very rarely, enough to actually switch the output answer. So you can't switch the model to saying, yes, I'm being steered, someone's manipulating me. But by looking internally at these probabilities, we can see, okay, what's going on is I'm being manipulated. And so the question that this work prompted me to look at is this question of where else does this sort of introspective behavior happen? And what might that teach us about how models are doing computation internally? And so the question that I'm going to talk about today that I have some, I think, very cool results on is this question of if a model can detect if we remove layers from it. So the idea here is because language models work with this sequential computation through layers. You can take the same question of are you being steered or a broad family of has a concept been injected? Is there anything funny going on? Any sort of question that maybe you might nudge an actor to say something is going on inside that might have changed. We can take any of those questions and run through and calculate probabilities. And we can do the same thing, but just cut out a bunch of layers and see if the answer changes. And so getting to some, before we get to some initial results on this, because I think it's a pretty straightforward experiment conceptually, is I'm testing this on Quen 2.5 with 32 billion parameters. And a thing you really need to know here is that it's 32 billion parameters, which is kind of low to mid-size for language models today. So most language models you can interact with through, say, Anthropic, OpenAI are going to maybe be half a trillion parameters or more, so maybe 10x or more the size of this model. It's still pretty big. 32 billion parameters is enormous by the standards of anything pre-2017. And we got 64 layers. So we got 64 different layers to work with and move apart. And I'm using this model because it's great for comparison because that's where previous work in the literature is. So initially, when I started this work, it looked like the model might actually be doing some introspecting. So I've whited out this graph just to get you oriented on the axes before I show you this heat map because it's a little bit complex. But as we go up on the y-axis, you're going to see how many layers I'm removing sequentially at a time. So we remove either 1 up to 16 layers. So 16 layers being a full quarter of the width of the model. And then going from left to right is the starting point where we start the ablation. So if I started at layer 8 and I had width 8, then that would say I would remove layer 8 through 16. So the model would just shortcut and jump from layer 7 to layer 17 and then continue its computation all the way through to the end. And so what do we see? We see kind of a weird pattern. So we see that in this early chunk from, say, layer 8 to 20, we see that slicing out big chunks of these layers cause the model to be much less confident that it's being steered. So the model is going to say, no, there's nothing going on. Everything's completely ordinary. And then here in this layer 24 to 40 range, give or take, we see that what happens instead is the model becomes increasingly confident that something is being manipulated. And so there's also some interesting outliers. For example, this layer 0, so the very, very first layer, shows up to the first set of up to, say, 6 layers removed. The model is extremely confident that you have done something to it. So if you take out the very, very initial part of the computation, the model is significantly more confident that something funny is going on. And there's, again, similar effect in, say, maybe layer 4 up here when you're slicing out a full quarter of the model. And so this is cool. It's kind of a maybe big question mark of what's going on here. Maybe there's some early mechanism in the model that's involved in sort of reinforcing the no answer and something in this second chunk that's involved in reinforcing the yes answer. But as I was being the good scientist that I am, I went ahead and ran some controls. And this effect also shows up in controls. And so the weird thing here is that it looks like rather than this being a introspection behavior, what might actually be going on here when we slice out entire big chunks of the model is that the model has some sort of internal yes no response machinery that is distributed across layers that we are affecting. And so it could still be introspection. Again, the term introspection is a little bit underdefined because, we're sort of anthropomorphizing a large language model. We don't necessarily know that they think or reason in the same ways that humans do, and that's a different philosophical question. But the fact that this showed up in controls raised a lot of questions about the underlying mechanism that might be happening. So then this probably isn't introspection. It might just be a binary yes/no mechanism in the model. What's actually going on? And this is where we're going to get to some of the more mechanistic interpretability results for this. So, like I've talked about, certain sets of layers here create the most change. So we got this sort of not yes chunk, which sort of down regulates the model's confidence that's being steered. We got this yes chunk that upregulates it. And so the question that I want to answer here then is what specific neurons are involved in the changing computation here? And the way to do that seems almost embarrassingly simple, which is we can look at exactly which specific neurons change. So we take the model's ordinary generation, which is usual, and then we take the model's generation when it has been ablated in some way, and we just calculate the difference at every single neuron in the activations. So it is literally just take the model in two conditions and subtract the difference between the two of them. And what this gives is how every neuron in the model changes when we remove these layers. And when I do this, I get a weird result. So again, I've sort of whited out these graphs just so it's easier for us to flow through them. But I do this in three different scenarios. So I do a contrast against this layer 13 through 28. So that sort of no shift region, layers 30 through 41, that yes shift region, and then layers 0 through 3, which is where we see it, that big, high confident yes jump. And so what we see is that the neurons, so here on the y-axis, this is just where they're positioned within the layer. That's kind of arbitrary. It just makes it easier to see how many of them are in each layer. And the x-axis is the position in layers. So when we calculate this contrast, so just this pure difference of what are the things that are most highly changing when we knock out this chunk of layers, we actually see that these things are super localized to the end of the model. And this is true whether we do it with this no shift region, this yes shift region, or this very, very early region. And there are some aberrant chunks right here. So maybe on this layer 0 through 3 region, there's a few very, very early neurons that are changing significantly. But it's weird, right? We would expect that if we are removing this big chunk of computation, then maybe there's like distributed computation afterwards that is involved in recovering or maybe like realizing that something has changed computation in the layers. But doing it this way, where we look at, and I should say, these neurons are the top 0.1% of neurons by change. And so this is just a sort of arbitrary valued thresholding that's been used in other works in the literature. So top 0.1% of things that are changing. And so the other thing that is interesting to notice is that in all of these cases, and I have support equals 2 and support equals 3 listed because that is how many replications of different question formats this change is robust in. But the change is always identified after the ablation occurs. So we never see that there's a neuron that is affected earlier than removing the chunk of the model. And this makes sense, right? If there is some mechanism that's changing downstream, we expect that only the subsequent computations could affect this. So you got a bunch of neurons that seem to, in some way, be causally related to this answer shift effect that we see in both the yes and no direction. I see that about 90% of the neurons across these three sets, despite them changing the answer direction in dramatic ways, are completely shared. So this points to maybe there being some shared answer machinery going on. And to really bring this home, tighten it up a little bit, the next thing that I do is I run a intervention just using these neurons. So we take the full model, full computation, and we just nuke these neurons to zero. We take them all the way down, we zero them out in the model's computation. And if I do that, then we see that, in fact, it does change the model's answer preference from no to yes. And so the units here are somewhat arbitrary because we're working with very small probability, so we're working in log space. but compared to a random set of equivalently sized neurons in the background set, you see that this effect happens not just in the yes no case, but also if you change the question format such that it is true false or AB formatted or any other generic binary choice answer.
Can I ask a question?
Yeah.
Well, what is the step between the final layer and that final probabilistic distribution? Like, is there an instruction in the order of operations when it's when this, I don't know, what is it, data is passing through each layer? Once it hits that last layer, how is that interface with then your output? Like, is why would the last layer have it see the most of the impact from this?
So I think there's two answers there. So what happens at the very end of a language model is we have a final step that takes us from the very, very large internal tensor. Let's just think of it as a vector representation that is a very high dimensional, just numeric representation, and takes it to a probability across tokens. And so that takes it from whatever the model width is. I think in Quen 2.5, it's on the order of, let's see, so it would be, call it 20,000 numbers. So think 20,000 numbers that have been manipulated through this entire stream. And then we have a final layer that takes that to whatever the size of the vocabulary is. So our vocabulary is going to be a few 100,000 items. And so when we do that, we just reduce it to a normalized probability. And that is just learned through gradient descent. So we force it to be a probability, but that actual probability distribution is entirely the softmax function ending up coercing the probability of all these n things to sum to one. As for the why is this biased in the end of the model, I have two potential answers, and actually, I was going to get to those next. So, mechanism doesn't have a great explanation, but I have two different hypotheses for what might be going on here. So, the first thing is we know that language models have a lot of redundancy in late layers. So, we have seen across, even from early language model research, that if you take certain circuits that are capable of certain functions and you selectively remove them, then frequently models will have redundant circuits that are capable of performing the same task. And so the most sort of benign answer here is that the model has a redundant mechanism for binary question answering because binary question answering is a pretty common task in language. And especially if this is a model that's trained for sort of LLM chat usage, which this one is, then it's going to have a lot of maybe like evolutionary pressure isn't quite the right word, but that's a good way to think about it. Pressure to have redundant mechanisms to answer yes no questions. And the other thing that might be going on here is because I see that this is sort of stable across both yes, no, true, false, A, B questions, that maybe there's just some late in the model binary answer mechanism. And what is happening is through the model's computation, it collapses the probability of this at the end. So, right, maybe across all the computations going on, it is sort of up and down regulating whatever stuff it's doing internally. And then when we get to the very, very late stage in the model, whatever computational mechanism has been learned, decides, okay, this is a binary question, so I need to collapse this down to a binary yes or no answer. And so it
It
could just
sounds
be,
like an
yeah,
all or nothing, like a neuron.
yeah. Well, what's the question?
Well, it wasn't a question, but it almost sounds like an all or nothing firing at the end if it's a binary question.
Yeah, it could be. And so it's maybe not an individual neuron, but here we're looking at a set of like 200 to 300 neurons, which considering that each layer has, 30,000 neurons is a very, very small subset of behavior. And there's actually been a lot of recent research coming out started this year that suggests that, in fact, that is probably the case, so that we can think of a lot of behavior as being sort of these sparse bases inside these MLP layers. And so maybe what this is just by doing this layer-wise removal of the model, what we have actually just identified is the binary response function in the model. And so I'm still working on this project. I have my primary work is on developing conditional dependence graphs to basically identify the structural relation between neurons. And so I'm working on that right now. The next step is to take these sets of neurons and say, okay, how are these neurons structurally wired together? And then can we see if this binary answer format exists before and after fine tuning? Because since this is an open model, we have the generic base model that's just trained as an internet text predictor, and then we have the chat trained model that is trained to actually engage in conversations. And so in a different context, I have seen that you see basically in mechanisms like this complete rewiring of the connections between these neurons before and after fine tuning to be a friendly assistant. And so I'm excited to see how that shakes out. But at this point, this is sort of a big question mark on what's going on with this generic binary answer mechanism. But I think it's a cool causal story because we started with this hypothesis of, okay, maybe the model can detect what's going on. And then we've actually found a pretty small set of neurons that seem like you can just slam them up or down to change whether the model answers yes or no. And the thing is, I have also seen in some testing that this yes no shift is not just true in the case of questions about internal model state introspection, but it actually also works in questions of true factual questions that should have really, really solid responses. So, for example, if I ask, is the sun a star? And then I apply a really, really strong vector on this, we can't quite shift the answer, but we can, 400, 500x the probability that the model is going to say, no, the sun is not a star, which is kind of weird, but also a cool mechanistic thing to find. And so with that, that's all I've got right now, but I'm happy to chat and answer any questions you might have.
Zach, that
Hi.
was super,
Oh,
super
sorry.
interesting. Thank you
Oh,
very much.
thank you.
Hi, this is Maciek. I wanted to ask, 'cause I don't do research on LLMs. I was
Yeah.
just wondering if um, after this ablation, c- does the model not answer like in a different language, for instance? Do you somehow are able to control for this?
So in this context, no, the model does not answer in a different language. However, we could go ahead and do this same thing on different languages and probably pull out a similar like language vector. So you
Uh,
could
uh,
say provide, say, like English and French responses in the affirmative and negative, and see if we could control first for like a generic, say, French versus English language vector, and then maybe say, okay, is there a distinct French versus English binary answer vector? Or maybe, and I suspect this would probably be the case, if we did this in a different language, we might capture the same binary answer mechanism that we found here. So that'd be a cool experiment. I haven't run it. I know that actually, I think yesterday or 2 days ago, uh, Goodfire put out a paper where they were able to show that with minimal intervention in sort of an adjacent method, they were able to completely remove model's ability to speak German with minimal effects on other languages.
hmm.
So that's definitely a idea that's out there that this and adjacent interpretability approaches are able to do right now. And a lot of what interpretability is at right now is sort of iteratively refining how fine we can get with our steering because there's especially in the early methods there were a lot of off-target effects, but as we sort of get more mechanistic and more sparse, we're able to really pinpoint these exact mechanistic things that are going on.
Oh, thank you. And do these models uh, like think in a different language in the sense that not in all languages that we have these clear binary responses. Like in some languages slash cultural circles, like there's more nuance, even to like binary stuff because it's trying to not to be too categorical is sort of the how you should be speaking.
Yeah, I think so. describing how models think internally is a tricky question to answer because they are just piles of math. And so what's going on is the model at each step uses a mechanism called attention to decide basically the pairwise importance of each word in your input. And
Oh, yeah,
so,
yeah, I
yeah,
understand
yeah.
that. I was
Okay,
wondering,
yep.
like, in what language do they? So, in this case, if they are fed a vector in a different language, so they or text in a different language, then they have a different vector. So, it could plausibly lead to different inferences just based on the language.
I see, I see. Yeah. So I think that's definitely that is a very interesting question because I think what we need to probe more, and that I think there is increasing evidence for, is that models sort of organize linguistic specific functions and general sort of like abstract question answering functions separately. And so maybe what's going on in terms of internal representations is that if you ask a question in French, then you are activating the French set of MLP neurons, as well as the binary question answering mechanism. And so your output will be in whatever your language of choice is, but perhaps the underlying mechanism is still the same computation because there's no pressure
Mhm.
on the model to maybe learn a redundant version of yes no answering if it can just say yes no answering and then
Yeah.
across these different languages we just point to the same circuit.
Okay, thank you.
Yeah.
Zach, this is a Chinese model, right? So,
Yeah.
um, can you do any interesting mech interp work around the fact that it almost certainly has been fine-tuned for, specific political uh, requirements?
Yeah, so I can shift a little bit, and this actually lines up pretty well with some different research I've been doing, but I will
Okay.
back
I,
up
I did
to,
not know that. I'm not cheating in my question answering here.
no, no, you didn't know that. But so if we're looking at, right, this steering based on sets of these MLP neurons, which increasingly seems like a good way to do this because you can get very small interventions. I have been testing an approach to identified very efficient subsets of neurons that are able to remove, in the case of what I'm testing, alter refusal behavior. And so in a model like Quen, which I've been able to test on, I am able to see a significant reduction in refusal behavior up to the, depending on the size of the model, say like 80% plus reduction in how often the model will refuse, even on topics that would be aggressively fine-tuned.
Mm,
So in the case of Quen models, it would be things like, maybe things that are politically sensitive where the Quen models are made. But in the case of sort of generic model safety, you can also see that this reduces the ability to refuse for the case of maybe biosafety related questions. And the idea there is to use the fact that we can reduce refusal to actually induce the opposite or sort of strengthen these mechanisms, not to jailbreak models. That is not necessarily a safety oriented goal.
I think there's like interesting work to be done that has actually nothing to do with AI safety, also around kind of refusal and jailbreaking, um, more along the lines of like AI creativity. Like something I've run into, I've tried to use models to solve math problems in the past. I've experimented with all the, like harmonic and the other kind of AI
Yeah.
proof generator tools. And a lot of times, if I pose a question that is an open problem and they know it's an open problem, they'll just give up really quickly
Yeah.
because they're kind of priored by that knowledge. But I think many of these problems, like for example, the generalized star height problem is one that we had a talk on by Jean-Eric Pin presented it. It's like a famous problem in automata theory. My intuition is I think when we eventually get a proof, it's not going to be incredibly complex. I think it's just like you have to be quite clever to think of it. And so, but it might be within this space of only kind of, a couple pages of work, in
Yeah.
English, right? So I kind of personally believe that even current frontier models might theoretically be capable of generating that proof, but they won't do it because they think it's really hard, and therefore
Yeah.
the statistical prediction is that they can't do it. So
Yeah.
yeah,
Did you
that's
just force a keep going vector?
Right, exactly. It's something I've thought about. Like I've spoken a bit to my friend Brennan about like, could you do unlearning to like try to unlearn the knowledge that this is an open problem or something? I don't know.
Yeah, it makes me think of the recent sort of Fable uproar where people were very upset that they were going to do some parameter efficient fine tuning to just knock you back to a worse rendition of the model if it turned out you were trying to do any AI research. Well, frontier research, but all AI research is frontier research.
Right.
I have a question about your red and blue squares. Can you return to them?
These
Mm,
ones?
yes. So you said that we have different regions. So the first region is mostly blue, then it's changed to red, then it's going ahead and so on. But also
Yeah.
I see another behavior here. It's a saw-like graph. So it's going extremely up and then it's going down, like y equals 1 minus x, similar to
Yeah.
this. How this saw-like behavior can be interpreted and what does it mean?
That's a good question. I'm not sure how we would interpret the fact that it goes from negative to strongly positive. However, I would say maybe a cursory idea here is that maybe the model's default is that. Hold on, give me 1 second. I need to let my cat go to freedom. Go be free. All right, I'm back. So I would say that probably it could be that what's going on is the model has a default no answer to this question and it increases. I don't know, right? Because it's hard to associate. I don't know if we could generate that sort of line description here because we're slicing out individual windows. And so each one of these has only a very loose correlation to the next one, right? They're sort of independent sort of computational paths through the model. But that's interesting. I will think about that.
Why I saw this because it's in physics in electrotechnical circuits. It's like digitalization of some trigonometric functions. So it can go like squaring functions when you are going either completely up and then down, or you are increasing the um, increasing the charge and then extremely dropping it down. So
Yeah.
like one of the basic physical plots that I saw. And another question is that it's a mathematical one that pretty much you used a discrete derivative. So you subtracted from a model with more layers result for a model with less layers. So pretty much you took a derivative. It's one of the ways to take a numerical derivative, but there are other first derivative, but there are other ways to compute the first derivative, there are ways to compute second derivative, and so on. So you analyzed the first derivative in only one way, but what if you will try to compute the first derivative in other ways or to compute the higher derivatives? Maybe they can see you this long red stripes in some other shape or something interesting can appear.
Yeah, that's an interesting idea. So I think one idea there that might be analogous is here, let me go. I'll back up to our slide showing this, right? So we're calculating the difference, and then
Yes.
that can sort of analogously be thought of as taking a first derivative. So what we could do is what gets glossed over here is that this is looking at the perspective of only a single yes/no answer question. So sort of a single point in generation. And so what we could do is we could take this and then we could run it through a sort of fixed generation. So maybe take a sentence and do word one, two, three, four, five, whatever. And then that will give you a run of these differences and calculate the change over that. And it's not immediately obvious to me how that object would be useful for interpretability immediately, but it could be a fun idea, and I'm sure that there's something there that could be useful for the model. I think one of the really cool things about doing interpretability research is that because of the architecture of transformers, a lot of the ideas are pretty like straightforward linear algebra. And so you can really pull in a lot of toolboxes because most things apply cleanly to linear algebra.
There's
Well,
no
but you have idea for free what to take. So you can take subtract one number of layers and even more, and then take the sum of the first plus the last minus twice the middle. It will be second derivative and so on, and
I
see
see.
and see something like this. I don't know about interpretation, but you can see some obstruction, some artificial things that appear. Maybe
Yeah,
they can hint you the direction.
the compositionality of it could be interesting.
there's no like mathematical object that just directly kind of encodes or represents the probability distribution of a LLM, right? Like you just have to empirically see what the fuck you get out when you give it a bunch of inputs.
Yeah, I mean, it is the LLM is the object that encodes the probability distribution.
Right.
Right. And so you can shortcut at each layer and just take the final down projection that gives you the softmax and do that at any point in the model. And that's a bit of a hack because, right, the model has learned the full width. And so it really is the most true if you use the full width of the model. But we have found through like, and they call it like a logit lens or equivalent that you can just do this arbitrarily at any layer and say, hypothetically, what would the token be at this layer?
I see. But if you have like two models, like maybe modulo some questions about their shape or whatever, is there some way that you can just kind of in closed form compare the two of them writ large and get something that's equivalent to like the Melanobius distance between the distributions of their outputs? Or is that not really possible? Like, are you ultimately everything has to be kind of empirical?
No, I think so. I think the answer here is that it is a question of you ultimately end up being data set conditioned because LLMs are trained over the entire internet.
Mhm.
But looking at the output probability distribution is actually one of the ways that we have or people have identified in the past, like when people are ripping off models and
Right.
trying to pass them off as their own. And so, right, if I just take like a GLM and do some lazy fine tuning and then sell it as my own pre-train, then people can look
Yeah.
and say, actually, the distributions are basically identical in tokens.
Right.
And on the weight level, maybe I've changed the weights enough, but not
Like
enough for the,
the thing that the city of Rio did.
yeah, where they just merged two models 60/40. Yeah.
They took like the average of two models that were the same size or something.
Yeah. I think they just took the weights and did 60% weighting on one model and 40% weighting on the other model and just
That's so
stuck them
sick.
together. So,
I have a chicken or egg question.
yeah.
So if you phrase a question as like is it the chicken or the egg and then the chicken? Will it
Yeah.
bias the first one you give, or will it just choose one of them?
I don't know. I think that would be another fun little mechanism experiment. So the idea here, let me make sure I'm understanding this, is say we say the chicken and then predict whatever the next thing is, and maybe flip that and so
Or
say,
yeah, it's like
yeah.
flipping. It doesn't matter if you say like give me a true or false, or give me a false or true,
Oh yeah.
like
So
that type of thing.
yeah. So in my testing, I have seen that flipping the answer format does not change the preference
Okay.
here. So in the binary question format, where specifically we have a affirmative and a negative, it has sort of an inbuilt negative bias, or by default, it assumes a negative. And that's because if we say like even an A or B formatted question, you have to say A or B, like A, you're being steered, B, you're not being steered. And so it does not seem to be that the ordering there matters. And that makes sense because, right, attention is a many to many mechanism. So, like, why should
Yeah.
it be?
Yeah. I was just thinking like if the answers are really nonsensical, right, in
Yeah.
terms of like the pairings, then that would tell you something about the choice neurons.
Yeah.
If it does actually alter the choice by just like basic ordering or basic kind
Yeah.
of inputting into the model.
Yeah. So I don't think it is order affected, but I think more testing would be helpful there, right? More experiments are always better.
Zach, what's next for you? You've got a trip to South Korea. You are working on all sorts of interesting projects. I assume you're applying for like renewal grants with coefficient. You're
Yep.
probably applying for mats. Like what's in the future of Zach?
Yeah, so I'm applying for mats. I made it to the very last round last time, but didn't get in. So I'm applying again. We'll see. You never know.
Yeah,
Looking for more funding. I have this workshop at presentation at ICML, which I would like to brag is I got a spotlight talk on. So that's pretty cool. It's not a
that's
full
awesome.
workshop paper, or it's not a full conference paper, but it is a workshop spotlight, which is pretty cool. And so, just the always looking for more funding, independent research grind. I think what's next is I have some really good steering results building on some of the ideas discussed here today, a little bit to the left because those are more mathy and theoretical, but probably trying to move things into like the RL safety realm. So, right, I have been spending a lot of time on structure of concepts and how to identify specific concepts and use those for downstream purposes. And so the question is, we've got all these, but steering vectors are not great in like a production model. So how can we take this and actually shove it into a fully trained model so that the behavior is instilled for safety reasons? So
Mhm.
there's that. And then my background's biology, so I'd really like to apply this to some like biosafety questions. So maybe say if we have sequence generation models, see if we can remove like a viral concept. So do the same contrast thing, but with say coronavirus sequences and benign sequences, and see if we can just wash out the ability to generate viral information. It's
And Zach, plenty of people I think on this call don't know why that's a problem. Can you like just quickly
Oh,
explain?
yeah, sure. So one of the problems that we haven't seen in the wild, but we're worried about is that DNA language models have gotten really good at telling you how to generate DNA or generating DNA sequences that are probably useful for building viruses. And so one could imagine in a bad future that someone could synthesize a novel virus that had far better capabilities in some X, Y, or Z way for targeting humans. Or I think what I really worry about is like the crop safety angle of it because crops are such a monoculture. But the idea is if we're going to have open models, then we want to be able to sort of mitigate the ability of bad actors to use synthesis models to generate novel viruses and other pathogens, right? We don't want another pandemic or another kill everybody.
So if people watching this afterward or now are interested in that problem, they should definitely hit you up. They should also go talk to Coefficient Giving, which is giving quite a bit of money to try and solve these problems. If you are a smart person and you have ideas for how to stop terrorists from printing viruses, you should go talk to Abby at Coefficient Giving, and she will perhaps fund you. Um,